Hello and welcome back to the Science of Concrete Materials class. This is lecture number 12 of the class. We are still on the cement module of the class, the hydration and microstructure. And today's topic is the calculations of the volume changes of the paste, solids, and voids. Just to be thorough, I will mention here the background of the calculations of the solids and the pore volume. Knowledge of the porosity can be very useful since porosity has such a strong influence on the paste properties, particularly the strength and the durability. Okay, so as we said, this is an important aspect of the microstructural development is the decrease in the porosity during hydration. Okay, so all the hydration products of the cement compounds have lower specific gravities and larger specific volumes than the cement compounds themselves, as you can see in this table right here. Okay, so that means every hydration reaction is accompanied by an increase in solid volume. As I said, knowledge of the porosity can be very useful since porosity has such strong influence on the paste properties. Particularly the strength and the durability, as we will see in the next set of lectures within this module. The total porosity in the paste, but not the pore size distribution, you have to make this distinction, can be calculated quite simply. It is possible to calculate the volume changes and hence the porosities from the chemical equations describing the hydration using the specific gravities of each species, if the composition and the fraction of hydration of the Portland cement hydration of each compound are known. But instead of that, a simple set of equations was proposed by T.C. Powers, which can be applied to all Portland cements, types 1 through 5, and which help us avoid the more rigorous and complex calculations. These equations are empirical in nature and derived from the experimental data. These equations, can be easily solved, if the amount of cement, if the amount of hydration of the cement is known. The volume relationships among the constituents are presented schematically in the figure shown on the next slide. So basically, by ignoring the actual makeup of the microstructure for simplicity, the hydrated cement fraction includes all the hydration products, the calcium silicate hydrate, calcium hydroxide, and the sulfur aluminates, without distinguishing them separately, so that you have to keep this assumption in mind. This is the figure I just mentioned here. This is just a schematic to represent the concept. From this schematic, you can see here, for example, in figure A, this, represent the hydration of a cement with the constant water cement ratio of 0.5. And we see the changes, let's go back. We see the changes that occur as we increase the hydration. Alpha here represents the hydration from 0 to 1. As you can notice, as the hydration increases, the volume of the solids here increases. The unhydrated cement decreases. The hydration products, or the hydration products, increase the solids volume. And you notice the capillary pores, the presence of the capillary pores. And figure B here, we fix the hydration, which is a full hydration, and change in the water cement ratio. As you can see, as we increase the water cement ratio, of course, the hydration increases. And look at the hydration products here. Look at the gel pores, almost constant. And look at the capillary porosity. As we increase the water cement ratio, the capillary pores volume increases. Okay? So from the schematic figure here above, two types of water are distinguished. The evaporable water, look at it here, right here, which is the gel pores and the capillary. The evaporable water is lost when the saturated paste is de-dried or oven dried. And the non-evaporable water is lost only when a de-dried paste is heated or ignited to 1000 degrees Celsius. The evaporable water encompasses the water held in both capillary and gel pores, including the interlayer pores, as well as some hydrate water from the calcium sulfoaluminates. The non-evaporable water approximately measures the amount of water combined structurally in the hydration products. That's another, fixed assumption that you have to be aware of. The non-evaporable water, denoted as W sub n, is proportional to the amount of hydration that has occurred. So, which is about 24% of hydrated cement. So according to this equation, W sub n equals 0.24 times alpha, which is the degree of hydration, a gram per gram of the original cement. Okay, so this is in terms a fraction of the cement that has hydrated. When the cement is fully hydrated, meaning alpha is equal 1, 0.24 gram of non-evaporable water is combined with each gram of cement. Okay, so equation 1 is used to determine alpha experimentally. The amount of evaporable water associated with all the hydrated components, meaning the water that is held in the intrinsic porosity of the cement gel, meaning the gel pores, which also includes some hydrate water from the calcium sulfoaluminate, is given by this relationship, which is denoted W sub G, equals to 0.18 times alpha gram per gram of original cement. W sub G is the gel water and is primarily associated with calcium silicate hydrate. This is equation number 2. Another equation, which is the total volume of hydration products, the cement gel, is given by this equation number 3, which is denoted by V, capital V sub HP equals 0.68 times alpha, cubic centimeter per gram of original cement. So the volume of the gel pores, V sub G, is also determined, from equation 2 above as a cubic centimeter per gram of original cement, since basically the specific gravity of evaporable water is effectively 1. So that's easy to determine. The gel porosity, capital P sub G, expressed as a fraction of the volume of the hydration products, V sub HB, is given by this equation number 4, which is P sub G equals W sub G divided by V sub HP, which equals to 0.26. This fraction is a constant value for all normally hydrated cements. So about 1/4 of the volume of the hydration product is pore volume. The capillary pore volume is given by this equation number 4. Okay, I went too fast. Which is V sub C equals W over C minus 0.36 alpha. You know, where W is basically the original weight of water used from the paste, and the W over C is therefore the water cement ratio by weight. And the capillary porosity is, you know, strongly dependent on the water cement ratio. Okay, so the volume occupied by the unhydrated paste is equals to 1 minus alpha times V sub C, small v sub C, cubic centimeter per gram of original cement. You know, the V sub C is the specific volume, which is the reciprocal of specific gravity of cement, and it is approximately 0.32, knowing that the specific gravity of cement is 3.15. So before hydration has commenced, the V sub U is simply equals to V sub C. So the original volume of the paste is represented by this equation, V sub P, which is equals the water cement ratio plus V sub C from the above equation, expressed in cubic centimeter per gram original cement. So the water cement ratio of the paste is increased, its capillary porosity increases. So the capillary porosity is expressed in this equation, this expression in equation number 7, which is denoted P sub C, which equals capital V sub C divided by capital V sub P, and it's equals to the water cement ratio minus 0.36 times alpha over water cement ratio plus 0.32. Powers also use the gel space ratio, which is a measure of capillary porosity, and is defined as follows: denoted X, and which equals the volume of gel, including gel pores, divided by the volume of gel plus the volume of capillary pores, and this reduces to 0.68 alpha divided by 0.32 alpha plus the water cement ratio. This is equation number 8. So using these set of equations 1 through 8, it is possible to calculate the volume of the paste constituents for the varying values of alpha. This is supposed to be alpha here, the degree of hydration, and the water cement ratios. This really was done to construct that figure shown earlier right here. Okay. So these calculations, you have to keep in mind, these calculations, you know, assume that no overall expansion occurs and the pastes are hydrated at or near ambient temperature. These are the assumptions that used to develop these models. It is also assumed that the pastes are hydrated in a sealed condition, that is, with no additional water added during curing and none lost by evaporation. Okay? And also, as you see from the figure shown previously, and I'm just showing it here for reference, it clearly shows the marked effects that water cement ratio and alpha, the degree of hydration, have on the capillary porosity, as indicated in equation number 4, if you go back. So here really a sample of calculations for water cement ratio equals 0.5 and a degree of hydration of 0.75. So we will be able to calculate all these parameters. If you see, the non-evaporable water equals 0.24 times 0.75 and equals to 0.18. This is gram per gram of cement, and so forth. You know, if you check these out and go back and apply the equations one by one to figure these parameters out. So basically, this is what I wanted to introduce, these set of equations, to give you a sense of how we calculate the hydration products, knowing the water cement ratio and the degree of hydration. Okay. One thing I wanted to this thing is going too fast. Sorry. One concept I wanted to introduce, which is the minimum water cement ratio. At low water cement ratios, there is insufficient space for the hydration products to form, so that complete hydration is not possible. Using this criteria, you know, the minimum water cement ratio that can be used and still ensure complete hydration can be determined from equation 4 by setting P sub C to 0 and the alpha degree of hydration to 1. The value comes out to be 0.36. However, the hydration products must be formed with gel pores saturated. So the water required for complete hydration is as follows from equation 9a, which is the water minimum equals the non-evaporable water plus the gel pores, gram per gram of original cement, or as shown in equation 9b, this value equals to 0.42 times alpha, the degree of hydration. So for complete hydration, where alpha equals 1, the water cement ratio should not fall below 0.42. Remember this value, okay? By this, you know, we come to the end of lecture number 12, and next time we are going to start on the following topic, which is the microstructure property relationship. This is a more of a practical topic to relate everything we learned about the hydration process, the development of the microstructure, you know, the solids and the voids and the other components, how it relates to the properties of the paste that we see and feel. Okay, until next time, thank you for watching, and I will see you next time.